Welcome everyone to this sixth tutorial session of Structural Analysis-1. Today I would be covering uh, influence line diagrams. Uh, so I have a mixed bag of questions and I will try to address. And I'll try to address the concepts covered in the class through these questions. So I am Sukanya Karmakar. I am a second year PhD student at IIT Kanpur. I mainly work in the field of earthquake engineering. So let's start this session. So this is the first question that we have to draw the influence line diagram for shear force at point C for this following beam. And then a second part of the question is there. So let's first address the first part of the question, which is drawing the influence line diagram for the shear force at point C. So first, I'll use the more traditional, calling it traditional method will be wrong. The first method which was discussed in the video lectures, and then we'll move on to the Mueller-Breslau method. So starting with the first method, this is the beam given. Fine. Now, to draw the ILD, first in ILD, like what are we drawing? Basically, there is a moving load. We consider it to be a unit, a load having unity value. A unit load is moving on the beam, and we try to calculate the various responses of the structure. Like you can draw the ILD of reaction forces, that is the support reactions. You can draw ILD for bending moment at various locations. You can have ILD for shear force diagrams, for shear force, sorry, calling it diagrams would be wrong. You can draw ILD for shear forces, for bending moments. So it's a varied thing. So basically you have a unit load of 1 kilonewton, and let's say it is at a distance x. So and let's say this is the beam. Let this reaction be AY. Let this be BY. A unit load of 1 kilonewton is acting. This distance is x. This is A, B, and C. Now first, I just want to calculate the support reactions. What will be the value? So I am taking the moment about point B is equal to 0. So AY into, let for the time being this length be L, and let this distance be equal to A. Then I'll put the corresponding numerical values. I'll just plug in the values and get the answer. So AY into L, taking moment about B, I'm taking clockwise moment to be positive. So AY into L minus 1 into this distance will be L minus X is equal to 0. So AY is L minus X by L. Fine. Similarly, summing up the force in the vertical direction, AY plus by is equal to 1. From there, by is 1 minus ay, which is 1 minus L minus x by L, which is L minus L plus x by L, which is x by L. So, we got these two reactions. Then, what do I want to do? I want to calculate the shear force at point C. So, for that, what will I do? First, I'll consider the case when this x means this x is less than 14 meters, or the x is less than a. That is, the point load is on the left hand side of point C. It is on that portion of the beam. That is case 1. So uh, first I'll consider the situation when this is A, this is C, this is B, and the unit load is to the left side of C. So we already have the reactions of AY and BY. So consider this portion. Here you already know what is BY. And see, if you take an element at C, here according to us, this is the sign convention of positive shear. So with that sign convention, VC will be in this direction. This is positive VC with this sign convention. So here VC is equal to minus BY. VC is equal to minus BY. From where that we get this summation of force in Y direction is equal to 0. And BY is x by L. We had already calculated this here. So, and here x is varying from 0 to A. What is A? This is A. Next, I consider the situation that when the unit load is on the right hand side of, like it is lying in the portion of the beam where x is greater than A. So this is A, this is A, C, D. So now we'll consider, let's say, this portion. We know the value of AY, and let this be element C. So this is the sign convention which we are considering. So positive VC will be in this direction. Why downward? Because on the element, if it's in the upward direction, on the beam it will be in the downward direction in order to maintain equilibrium. And fine, this and there also will be a moment at C. I had not written it earlier because ideally it should be there, because here I'm drawing the equilibrium and the free body diagram. So now again I'm summing the forces in the y direction. Then AY minus BC is equal to 0, or VC is equal to AY. And we had calculated AY to be equal to L minus X by L. So here AY is L minus X by L, where X varies from A to capital L. What is capital L? This is capital L. So now we have the expressions for VC. So VC is equal to minus X by L when X varies from 0 to A, and it is equal to L minus x by L when x varies from A to L. So with this, we can draw the diagram. So if this is A, B, C, this is A, this is L. So when x is between 0 to A, that is in this portion, the equation will be minus x by L. Means when x is equal to 0, it is 0. And when x is equal to A, it is minus A by L. So in the downward direction. And here A is equal to 14 meters. See, in this question, this is what I'm referring as A down. So A is 14 meters. And L, total length of the beam is 20 meters, because what is this total length? L will be 14 plus 6, which is 20 meters. So how much is this? This is A by L, that is 14 divided by 20, which is 0.7. And in the second equation, this being the first equation, this is what I obtained from the first equation. And in the second equation, if you put x is equal to capital L, again it is 0. And if you put x is equal to A, then it will be, this will be L minus A by L, which is 20 minus 14 by 20, which comes out to be 0.3. So this is the ILD for shear force at C. So this is using the first technique, using the long method. So is this clear? Okay, we can take doubts at the end of the question. So we can also use the Mueller-Breslau principle to draw this shear force diagram. How will we use the Mueller-Breslau principle? So what does the Mueller-Breslau principle state? It simply states that you release the suppose you have to draw in this beam, you have to draw the ILD for RA. Then you will remove the restraint at A, and you have to draw the ILD for the vertical reaction at support A. Then you will remove the restraint in that direction. Means you will allow the beam to move in the vertical direction, and you will give a unit displacement in that direction. And the deflected shape of this beam will be same as the ILD, the influence line diagram for that reaction. Here we have given a unit displacement for calculating the influence line diagram for the vertical reaction at support A. Had it been suppose at the point C, you have to draw the influence line diagram at point C for the bending moment. Then you have to remove the restraint. For moment, what is the restraint? Basically, you are allowing the rotation at that point. So you will have to provide a unit rotation at that point. So, and like here I'll have to draw the ILD for the shear force at C. For shear, like when you're removing the restraint against shear force, basically you are allowing the beam to slide. So that is the restraint here. You will allow the beam to slide at that portion. So suppose this is that beam. For convenience, I'm drawing it again. A, B, and C. And here at like for us, positive sign convention for shear is this. So at this end, you are allowing to move it down, and this end, you are allowing to move it up. Basically, you are allowing sliding here. So basically, you are allowing the beam to slide here up on this end, and on this end, you are allowing to slide it down. Sorry. And here, the total slide, like if this much portion is x and this much portion is y, the total of x and y should be equal to 1. Also, when it is sliding, these two lines will be parallel to each other. So we can calculate x and y because this is the first relation how they are related, and also since these two thetas are equal, you can also write y divided by this is 14 meters and this is 6 meters. So y by 14 is equal to x by 6, or 3y is equal to 7x. This is one more relation. So putting 2 in 1, so you can solve that. You can put x to be equal to, sorry, I have made a mistake here. So this is 3, this is 7. So this is 3y is equal to 7x. This is equation 2. So from here you have okay, this is fine. From here you can write x is equal to 3 by 7y, x is equal to 3 by 7y, plus y is equal to 1. So from here y is equal to 10. It is equal to 7 by 10, or 0.7, and x will be equal to 1 minus y, so 0.3. So this is equal to 0.7 and this is equal to 0.3. So using the Mueller-Breslau principle also, the ILD can be constructed and the values can be calculated. So the ILD is constructed. Now moving to the second part of the question. Calculate the maximum shear force at point C in the beam if a uniformly distributed load of 10 kilonewton a uniformly distributed load of 10 kilonewton per meter of length, 5 meter, moves on the beam from left to right. Sorry, from right to left. Okay, it is moving in this direction. This is the direction of the load, and the length of the UDL is 5 meter. Its intensity is 10 kilonewton per meter, and we have to calculate the maximum shear force due to this UDL. Now, this is the ILD. and we have to calculate. This is the ILD. Now we have to calculate the maximum shear force. How will it, and this length being, what is this length? This length is 6 meters. This length is 14 meters. So, uh, how when will the shear force be maximum? It can either cover the entire 5-meter length. Either it can lie in this portion, like it can lie here. Why will it lie here and not lie here? Because under uh, uniformly distributed load, how do you get the reaction from this ILD? You will have to multiply the area of this influence line diagram with the intensity of the load. Here, if it this since the length is 14 meter, if you start from the left hand side, then uh, the area under the influence line diagram will be less. But if the load is in, suppose, this portion, here this area will be higher. So, or either it can lie here. So we'll have to consider two cases. So this is the beam. This is point C, this is point A, this is point B. This is the ILD. This is 0.7. This is 0.3. This is 16 meters. This is uh, 6 meters. Sorry, this is 14 meters. Now, suppose the load is lying in this portion. Intensity of the load is 10 kilonewton meter. So, suppose this is case 1 and this length be 5 meters. And another load position can be, it can lie here. This is case 2. This is 5 meters. So from case 1, shear force at C, it will be equal to half into this side is 0.7. We'll have to calculate this. So how much is this? This height. So you can calculate it as like this height is 0.7 and the base being 14. This height is x, and how much is this base? 14 minus 5. How much is it? It is 14 minus 5 into 7 divided by 14. So it is 0.45. So 0.7 plus 0.45. And how much is the distance between them? 5 multiplied by the intensity, which is 10. So this comes out to be 28.75 kilonewton. Now considering case 2, shear force at C is half into how much is this height? This height is 0.3. Now, we can already see this triangle is small, so area will be less. So let's calculate it, but there is no point in doing it. And here the sign of shear force is negative, and here the sign of shear force is positive. So this being 0.3, the height is 0.3, and the base is 6, and this is 5, and you have to calculate like that side is 1, 6 minus 5. So basically it is 0.05. So 0.05 into 5 into 10. So this comes out to be 0.35 into 50 divided by 2. So it is much less. So the maximum shear force at C, maximum shear force at C is equal to 28.75 kilonewton. Okay. So is this question clear? Okay. Moving to the next question. Here we'll have to draw the influence line diagram for the shear force at point D in this beam. And this also has a second part that we'll have to calculate the maximum bending moment at point D of the beam due to live load of 5 kilonewton meter of span more than the length of the beam. Earlier, the length of the load was short, and now the UDL can cover the entire length of the beam. So basically here you'll have to draw the ILD for the shear force at D for as well as the bending moment at point D for the second part of the question. So uh, let's first draw the ILD for shear force at D. For drawing the influence line diagram for shear force at D, you first need the equation. Suppose a unit load is moving on the beam. You have to calculate the support reactions in terms of these, uh, in terms of the load position. So basically calculate the support reactions. So uh, let's start doing it. So this is the beam. Suppose for case 1, let the unit load lie here. Fine, this is a unit load, and I will calculate the support reaction. So first I'll calculate this, I'll take this portion. Let this reaction be dy, and here the reaction, this is C, this is B, and no unit load is acting in this portion. So let's take moment about point C and make it to be 0. Here I'm not, C is an internal hinge. So no moment is acting and there will be no moment at point C. So from here, by into 8 is equal to 0, or in other words, by is 0. Since by is 0, bc is also 0. Okay, let's write it. We don't need vc. So let's do by is 0. Now, consider the entire structure. On the entire structure, consider summation of fy is equal to 0. From there, now here you have by, here you have ay, and you have a moment in a. So ay plus by is equal to 1. By is 0, so ay is equal to 1. This I've calculated. So now consider what do you have to do? You have to draw ILD for shear force at point D. So now consider only this much portion. This is A, this is D, this is AY, this is MA, and VD, and you also have MD. Fine, and you have the unit load acting here, 1 kilonewton at a distance of x. Now here, do summation of Fy is equal to 0. Now here, Ay is equal to 1 plus Vd. So from here, Ay is 1, so Vd is equal to 0. And here, x is varying from 0 to 8 meters. This is true only when x lies between A and D. So basically x is varying from 0 to 8. So this is the first expression. Now x would be between point D and C. That is, x is varying between 8 meters to 12 meters. D, C, P. The unit load is lying here. This is x. This is 1 kilonewton. Fine. Now, again, calculate by. This is VC. No load is acting. Take this point C. This is point B. If you take moment above point C is equal to 0, you will get by is 0. Now, consider summation of Fy on the entire structure. So, this is AY. This is by, this is MA. So AY plus by is equal to 1. Now by is 0. So AY is equal to 1. So this is done. So now we'll have to develop an expression for VD. So again, consider this portion. Here you have AY, you have MA. VD will act in this direction, and there will be MD. Now, unit load is between D and C, so that does not appear. Now, summation of force in y direction is 0. So, AY minus VD is equal to 0. So, VD is equal to 1 kilonewton is equal to AY. So, it is 1 kilonewton. And here, X varies from 8 to 12. Crunched up everything here. Here x varies from 8 to 12. Okay, now this is done. Now x is lying between C and D. So that is x lies between 12 meters to 20 meters. B, C is internal hinge. This is point B. Now the unit load is lying here. This is X. This is unit kilonewton, one 1 kilonewton. So now here reaction is Vy. This is Ay. Moment is Ma. Now consider this portion. This is By. This is Vc. This point C, V, and you have a unit kilonewton 1 acting here. And how much is this distance? This is x minus 12. Is that small portion. Now take moment about c is equal to 0. From here you have dy into 8. This distance is 8 meters. Dy into 8 is equal to x minus 12 into 1. The load is 1 kilonewton meter. So how much is Vy? Vy is x minus 12 by 8. Now, summation of force in y direction is equal to 0. So, Ay plus Vy is equal to 1. So, Ay is 1 minus x minus 12 by 8. So, that is equal to 8 minus x by 12. 12 by 8. So this is nothing but 20 minus x, 8. Okay. Now you have a equation for Ay. Now I'll have to develop an expression for Vd. So how will we do that? Consider this portion. Ay is acting, Ma is acting, Vd is acting, moment Md is acting, right? So from here summation of force in y direction is 0. So Vd will be equal to Ay. So that is equal to 20 minus x by 8. And here x is between 20 and 12. So, so basically Vd is equal to 0 when x varies from 0 to 8 from here. So from 0 to 8 it is equal to 1 when x is between 8 to 12, and we get that from here. Get that from here. And lastly, we get one more relation from here, that is equal to 20 minus x by 8 when it is between 12 to 20. So now draw the influence line diagram. This is the beam, fixed beam, roller support A, D, C, D. 8 meters, 8 meters, 7 meters. Now drawing the between 0 to 8, ILD, VD is 0. Between 8 to 12, it remains 1. And between 12 to 20, it drops. When in this third equation, let this be first equation. This is second equation and the third equation. In the third equation, when you put x is equal to 12, it is giving 1. And when you put x is equal to 20, it is giving 0. So will be like this. This is 1 and VD is positive. So this is ILD for VD. You could have arrived at the same ILD using the Mueller-Breslau principle. So let's have a look at that also. So uh, in the Mueller-Breslau principle, what do? You release the restraint at that point and provide a unit uh, movement. So since I am allowing here, what is the restraint? You are basically, you you are drawing the ILD for shear force. So what does shear force resist? It resists the shearing motion. So here you are allowing the shearing motion and you are allowing the sliding here. So from the Mueller-Breslau principle, if this is the beam here, you are allowing the sliding here. Now here uh, A is a fixed support. And how can you move it down without disturbing that support? You don't want, you cannot allow any rotation at point A. So without breaking it, you can't move it down. So there will be no motion in the part AD. So the remaining part DCB, that will undergo motion. So this portion will move up by 1 since the total motion, the sum of both the displacements, like summing up both the movement, it should be 1. So since the entire motion is being, movement is getting concentrated on the right hand side, this will be 1. Now this C point is hinged. So once you push it up, DC will move up straight. Since it is like this, suppose this is hinged, and here beyond this another member is there. Once you move this by 1, the entire thing will shift up. So this becomes D, this is C, and this point is pinned. So the motion will be restrained at this point. So this is positive. So using the Mueller-Breslau principle also, we will arrive at the same answer. Okay. So this is done. So now the second part of the question. What is the second part? You have to calculate the maximum bending moment at point D of the beam due to the live load of 5 kN per meter of span more than the length of the beam. So first draw the influence line diagram for the bending moment at point D. So for drawing this, I am using the Mueller-Breslau principle. You can also use the other technique, but here I am using the Mueller-Breslau. So using this principle here only. So basically here you are, let me draw the beam once more. This is point B, this is point C, this is B, A. So at this point, you are allowing rotation. So as per our sign convention, this is positive. This is the positive moment. So the beam, it will be equal and opposite in order to remain, in order to keep that point in equilibrium. So how can you rotate the beam at this point? At the joint A is fixed. So you can't just rotate it like this. It will break. It has to remain straight. If you want to move it straight, then the slope at point A will change, but the slope at point A must remain 0. So there will be no movement in the part AD. But at point D, we are pushing it down. So it can move like this. And C is a hinge. And D, a point B is a roller joint. So at that point, the deformation will be 0. So it has to move up like this. Now, the entire rotation should be 1. No, there is no rotation in the part AT. So this theta will be 1. Since this theta is 1, this length is okay. I'm telling this length is 4 meters and this theta is 1. So tan from since this is 4 meters, even this height will be 4 meters. This height. So this is the influence line diagram for moment at D. You can arrive at the same at this ILD using this technique also, where you take the unit load, place it, and calculate the support reaction, then write the equation for moment. It can be done in that manner also. So what do we have to calculate? Calculate the maximum bending moment at point D of the beam due to live load of 5 kilonewton. And the length of this UDL is more than the length of the beam. So it will cover the entire length of the it will cover this entire length, and this is negative. It will cover this entire portion. This is because in the portion AD, ILD does not exist. So even if the load lies in that portion, it will not contribute. So this is 12 meter. This is load. This is the beam A, D, C, P. This is the load position. So maximum bending moment at point D, maximum bending moment at D is equal to area of the ILD half into base is 12, height is 4 into the intensity of the load. What is the intensity of the load? 5 kilonewton per meters into 5. So this is equal to 120 kilonewton meters. So is this question clear? Do you want me to draw this ILD for the bending moment diagram using the other technique as well? Or you can do it. Do you have any other questions in these two questions? The Mueller-Breslau principle and the other technique. Is there any confusion or doubt? I want you to try to draw
This
this.
for how these 4 meters is arrived, madam?
Okay.
ILD for ME, MD. How this
This,
depth 4 meters is arrived at C point?
yeah. This theta, this rotation is unity.
Okay.
If this theta is unity and this base is 4 meter, this has to be 4 meters.
What is this? It's like this 10:45.
Yeah, yeah. I'll write it down. Like, uh, calling the rotation to be basically calling the rotation to be unity was wrong here. I take my words back. It basically means this like tan theta is unity.
Okay, ma'am, okay.
Yeah, yeah. I used the wrong words here. If this is theta, then tan theta is okay. So a similar question. So here you will have to calculate the maximum bending moment at T at point D of the beam due to a moving load of 20 kilonewton per meter of span more than the length of the beam. Here, one speciality of this question is here earlier the points which you were considering they were lying on the beam. Now D is a support itself. So how will you solve it? So first step is drawing the influence line diagram. So I'll be using the Mueller-Bresler principle to draw the influence line diagram. So this is the beam. A, B, C. C is an internal hinge and B. And this is 4 meters. This is 2 meters. This is 2 meters. And using the Mueller-Bresler principle, now this is a sign convention. Like sagging moment is positive. This is a sign convention. So to maintain the equilibrium of the point, you are um, allowing your imposing movements in that direction, or you are allowing the beam to rotate in that direction. So is it possible to rotate AD without breaking it? No, it's not possible. You can't push it up. And like pushing it up as well as uh, like you cannot, since D is you can't allow it to move in the vertical direction. You can't, because it's a support. You are just allowing rotation at that point, but still of the restraint that a roller provides. A roller does not allow rotation in the vertical direction. That restraint is still there. So this AD portion of the beam, it will not move. So the only motion possible is in the only movement possible is in the portion TCB. So in the portion DCB, you're pushing the point D down. So you're pushing this down. And this point C is a hinge, so kink can form here, and this point B is again roller, so no movement is allowed at that joint. So this will move up. Again, at this point, if this angle is theta, tan theta will be 1. So basically, you are providing this tan theta is 1. So for like we had done previously, this is 2 meters. Even this height will be 2 meters. Okay. Now maximum bending moment at D due to UDL. What is the intensity of the UDL? 20 kilonewton per meter, and the length of the UDL is more than the length of the beam. So it will simply occupy this much portion, 20 kilonewton per meter. This will be half into base is 4, height is 2 into 20. So it is 80 kilonewton meters. Going to the next question. So in this question, says there is a wheel load of 20 kilonewton and it is moving on this beam from left to right. It's moving. What is the maximum shear force at point E, which is located at 3 meter right of support T? So I'm giving you 5 minutes, around 5 minutes time. So first, I want you to try this question because it's applying the same concept, drawing the ILD and then putting the load at the appropriate point and calculating the shear force. So first, I want you to draw the ILD. So I'm giving you 5 minutes time, then I'll try start solving. Here, I would like to make a small clarification. Like in question, this question regarding theta was raised. So here, what you are restraining, like you are drawing the ILD for moment. Moment restrains rotation, so you are allowing rotation. How much rotation are you allowing? You are allowing a rotation of unity. So you are rotating by theta is equal to 1, and we know that when theta is small, tan theta is approximately equal to theta. So if theta is 1, even tan theta is 1. So here, let me write it here. Let me put a note and write. Here theta is equal to 1. So here I am assuming theta is very small. So I can write tan theta is approximately equal to theta. Now theta is equal to 1. Therefore, tan theta is equal to 1. And from there, you can conclude that if this is 4 meters, then even this height will be 4 meters. From there, we get that. So please keep this in mind. Similarly, in this question also, theta is equal to 1. Tan theta is approximately equal to theta. So tan theta is also equal to 1. And from there, you get this height to be 2 meters. Okay, now you can try this question. Now, yeah, how will you draw IID for this? So I will use the Mueller-Bressler principle. The beam is 2 meters, this is 5 meters, this is 2 meters. you are allowing a motion like this. So this part, this A, D, E, this D portion, you are pushing it down. The point D is a pin joint. So there it cannot leave the joint and move. So there the deformation will be 0. So simply it will move like this, right? Similarly in this portion it will move like this. So is this clear? So like the parts of the beam it can't break. So if you are pushing the part ECB up, it will move like this. Sorry, I'm very sorry. Since you are pushing this up, it will move like this. Like ECB, the continuity will be maintained. And C is a roller joint, there also deformation is 0. So it will pass through this point. Now, we know, see, uh, let's refer back and let's put a note. But let's do some back of the envelope calculation. See, this is a simply supported beam. And suppose there is a unit load, sorry, at x distance, a unit load is acting. This point is A, this point is B. So let this be AY, let this be BY. So here we know AY is L minus X by L and BY is X by L. Suppose we have to draw the shear force at point C. Then we see when X varies between 0 to A, this being A, it is equal to minus X by L. And when X lies between A to L, it is this expression. Or in other words, if I draw it, the shear force diagram will be like this, where this portion is A by L and this portion is L minus A by L. So here also, what will be this value? This value will be, this length is 3 meters, this is 2 meters. This will be 3 by 5, which is 0.6. Is this number clear? Please draw analogy between these two cases. Here it is A by L, where A is this portion from the pin support up to C. So here from pin support, that is D, till up to E, it is 3 meters. 3 divided by the entire length of the pin between D and C. So it is 3 by 5. And how much will this portion be? This portion is the remaining L minus A by L. What is L minus A? This portion is L minus A. The remaining portion of the beam, what is that? That is 2 meters here. So, yeah, it is 2 by 5. So, that is 2 by 5 means it is 0.5. How much is this? Can someone calculate this? Let me call this X dash. Can someone calculate this? You can simply use similarity of triangles. This triangle is similar to this triangle. Since this portion is a straight line, how much will that be? Yes. Yes, true. That will be equal to 2 by 5. That is 0.4. And similarly, what will this value be? This value will also be 0.4. Since this is 2 meter, this is 2 meter, this is 0.4. Now, here also we can see this is negative shear, this is positive shear. So this is negative shear, this is positive, this is negative, this is positive. What do we have to calculate? Now, we will have a wheel load is moving from left to right, and we have to calculate the maximum shear force at point E, which is located here. So where will you place the load? Where will you place this load of 20 kilonewton on this beam in order to get the maximum shear force? Where will you place it? Any ideas? You will place it at point E itself, and to the left side of point E or to the right side of point E? To the left. Why to the left of E? Because from the influence line diagram, we can see that the ordinate is 0.6 and on the right side it is 0.4. Yes, it should be to the left of E, because how do you calculate a response from an influence line diagram? Again, I'm iterating it. You multiply the value of the load with the ordinate. Since it's a point load, you take the point value of the point load and multiply it with the ordinate which you get from the influence line diagram. So it should be placed on the left of E. So therefore, let's keep this, let it be like this. So let's write this fact down, that from the file D, we can see that the shear force at E will be maximum when point load is located just left of point E. Therefore, maximum shear force at E is equal to 0.6 into 20, which is 12 kilonewton. So is this question clear? Okay, I'll move on to the next question. So now we have two loads. What does this question say? First, let's read the question. That if a two load system of 100 kilonewton and 20 kilonewton separated by 1 meter, okay, moves from left to right on the beam, so the loading direction is this. There are two loads. Moves from left to right on the beam shown in the figure below. Then calculate the maximum hogging moment at point E. The point E is defined. Note that 100 kilonewton follows the 10 kilonewton load. Okay. So what is in the, what load is leading? 20 kilonewton is the leading load, 100 kilonewton is the following load. So 100 kilonewton 20 kilonewton separated by a distance of 1 meter, and it is moving from left to right. So first, what will I do? First, you will have to draw the influence line diagram for the bending moment at point Q. So similarly, use the Mueller-Breslau principle and try to find it. So I'll give you around, I feel it's a straightforward question, so I'll give you around 5 minutes. You can solve it. I'm solving it parallelly with you so that you can match your answer. The concept remains the same. Use the Mueller-Breslau principle. You have to draw the ILD for bending moment diagram. So provide rotation at that point. Here again, you might be wondering what is this ordinate. This again, you can refer back to the simply supported beam and draw analogy from there. Suppose a unit load is acting at a distance of x. This is A, this is B, and let this be this be support B. C and at some point C. This A y will be L minus x by L, and dy will be x by L. And how will you write the bending moment? Suppose the load is lying in, suppose x is between A and C. So in this portion, PT, this is VC, and this moment is MC. So the moment MC will be dy into how much is this length? Let this length be A and let this be B. So this will be by into B. What is by? X into by L. So here X lies between 0 to A. And suppose X lies in this portion, like beyond C. Then also expression for AY and BY remains the same. In this portion, you have AY, you have BC, and the moment MC. So here the moment MC will be AY. And how much is this distance? This is A. What is AY? L minus X by L into A. And here X varies between A to B. So this is the beam, A and B. This is point C. So M moment at C is equal to Bx by L when X varies between 0 to A. So when X is equal to 0, it's 0, and X is equal to A, it is equal to AB by L. What is L? L is equal to A plus B, and it is equal to L minus X by L into A when X lies between A, sorry, it should be, here I've written it wrong, A to L, A to L. When X is equal to capital L, it is again 0. When X is equal to A, this is like L minus A by L into A. L minus A is B into A by L, so it gives the same value. So what is this ordinate? It is AB by L. So here also the ordinate will be AB by L. Yes. 1.2, right? 3 into 2 by 5, 1.2. How much is this? How much is this ordinate? Use the similarity of triangle and find out. Sorry, I should have written it clearly. This is equal to 1.2. Now use the similarity of this triangle and this triangle to calculate this height x. So x by the base is 2, and here the height is 1.2 and the base is 3. So how much is x? X is 1.2 into 2 divided by 3. Yes, 0.8. Similarly, calculate this. Here it will be, let me put this as x dash. So x dash by 2 is equal to 1.2 divided by 2. So x dash is 1.2. Now, here you have two loads, 100 kilonewton and 20 kilonewton. Where will you place it so that you get maximum hogging moment? Here the bending moment is positive, here it is negative, and here it is negative. So either the load can be placed on this side in the portion AD, or it can be placed in the portion CB. So there are two cases. So this is the beam. This is A, D, E, C, and B. This is 3 meters, this is 2 meters, this is again 2 meters, and this is 2 meters. The ILT, I'm like redrawing it here. This is positive, this is negative, this is negative. So either you can place the loads like this. Now, in the question, it is given that 20 kilonewton is the leading load. So either you can, the 20 kilonewton can appear here and here, separated by a distance of 1 meter. This can be case 1. Or either the 20 kilonewton, here you have to calculate the maximum hogging moment. That is why I'm placing it like this. Or 100 kilonewton here, separated by a distance of 1 meter. So this is case 2. So I want you to, okay, for case 1, what is the bending moment? How much value did you get? Abhishek, you are saying case 1 is the correct one. What value did you get? This coordinate is 0.8. Here you can calculate the value. Again, using similarity of triangle, let this be x. So I'm solving case 1. The height is 0.8 over a distance of 2 meters. Let the height be x over a distance of 2 minus 1. So x will be 0.4. And again here, let this be x dash. I'll calculate that afterwards. So bending moment here, 100 kilonewton. Where there is 100 kilonewton, the ordinate is 0.8. And when the load is 20, the ordinate is 0.4. So what is the total value? It is 88 kilonewton meter. Now in case 2, again you will have to calculate the ordinate x dash. So it is how much? This ordinate is 1.2. So it is 1.2 over a distance of 2 meters. And the height is x dash. So again it is 1. So x dash is equal to 0.6. This x dash is equal to 0.6. This is equal to 0.4. So here bending moment is equal to 100 into 100 into 0.6 plus 1.2. The ordinate is 1.2 and the load is 20. This you get to be 84 kilonewton meter. So the maximum hogging moment at E is 88 kilonewton meters. Correct, Abhishek. It is 88 kilonewton meter. Now, moving to the next question. So, okay, let's do a lighter question first. Draw the influence line diagram for the beam given you. I want to draw the ILD for reaction at A. Use Mueller pressure principle. It will take only 1 minute. Quickly, we draw it. So, A, B, C, D. You have to draw the ILD for RA. How will you draw the influence line diagram? You will simply provide a unit display. You'll remove the restraint at A, which is restraining the motion in the vertical direction, and you will give a unit displacement. This will move up. Now at point D, it is a roller, so the deformation will be 0, and this will move down. Now C is a internal hinge, so this point will again move up because B is again a roller. So this is positive, this is negative. Now you had provided a unit displacement here. Can someone calculate this height, x dash, this height, this being x dash? Can someone calculate its value? What will that x dash be? Use the similarity of triangle of this triangle and this triangle and calculate x dash for me. Okay, I should have given the beam dimensions. This is 4 meters. This is 2 meter. This is 2 meters. Again, I'll write it here. This is 4 meters. This is 2 meters. This is 2 meters. Calculate the value of x dash. This value. How much will it be? Yes, it will be 0.5. So x dash is equal to. So this is ILD for RA. Now let's draw ILD for RB. You will provide a unit displacement. You first remove the restraint at B and provide a unit displacement. You push it up. Now C is a hinge. Suppose this is a hinge and you are pushing this up by. So there will be movement only in this portion. C, B. This is 1. This is plus. So this is ILD for RB. Is this clear? Okay. Next, we'll have to draw the ILD for bending moment at D. We have already drawn this earlier in one of the question. It's the same beam. So for the sake of completion, I'll write it here. So this is point D. So let me draw the beam here again. A, D, C, D. And you are allowing rotation here. This A, D point cannot move because D is a roller. You can't, you can allow rotation, but you can't allow movement. So this portion will move down. This portion will be like this. The theta is 1 unit here. This being 1. This height, this being 2. This height will be 2. This we had done earlier. So I am not explaining it much. ILD for bending moment at T. Now we'll have to draw the ILD for shear force at C. C is a internal hinge. Okay, I have drawn in the beam only this. This point is D. This is an internal hinge. point is to move down like this, this V1, this V does. This is ILD for bending moment at T. Now we have to draw the ILD for shear force at C. Shear force at C, that is the fourth part. Let's draw the beam once again. This is A, this is B, this is D, C. At D you have a roller. D, A, C, and C is an internal hinge. Here you are allowing sliding. So basically you can push this beam up. Now, without breaking the portion A, C, D, can you push up the joint C and maintain zero? Like first, you have to remember the motion will be straight, like straight line motion, and you have to maintain the deformation at A and D should be zero. Can you deform the beam with these restrictions? No. So the only motion possible is in the portion BC. So So the only motion possible, you can push this up, this will move down, and this is one. This is ILD for shear force. So is this question clear? Um, by prediction. Here, see, roller can provide rotation, but here at point D, in the left portion, you are rotating the beam in this direction, and in this direction, you are rotating the beam in this direction. So in the left direction, if you rotate the beam in this direction, you have to maintain zero deformation at point A, and the beam has to remain linear. For statically determinate structures, IL influence line diagrams are linear. These are straight lines. So if you are rotating in this portion, if you are rotating the beam in this direction, keeping the ILD diagram linear, you cannot rotate it in this direction. Like in this direction, if I push it down, how will the deformation at A remain zero? It is not possible. So the entire rotation is being provided in this direction, in the direction of DCP. So is this clear? Right. And linearity, why it is linear? Because it is statically determinate. You can check that this structure is statically determinate. Number of reactions is 1, 2, 3, and 4. So number of unknowns is 4, and number of knowns is, there are 3 equations of equilibrium and 1 equation because C is the internal hinge. So there are 4 knowns. So it is a statically determinate structure. Okay. So now this question. So this question reads, what is the absolute maximum bending moment on the following beam due to this three-wheel load system shown below? And it is given that the 80 kilonewton is leading load and the wheel is moving from left to right of the beam. And this is the system of loading which has given. So, first, since the loading is given, first we'll have to calculate the position of the resultant. And we know that like this was shown in the lectures, that if this is the centroid of the beam, and okay, let's first calculate the resultant and then I'll put that statement that what should be the position of this load on the beam in order to get the absolute maximum bending moment. So, so uh, this is the loading. There is a load of 100 kilonewton. Then there is a load of 60 kilonewton. And there is a load of 80 kilonewton. This is 1 meter and this is 2 meter. So first, what is the resultant load? I'm calling the resultant load R. That is simply the summation of all the loads, which is 240 kilonewtons. Now I'll have to calculate the position of this resultant load. So let the resultant load act at some x meters from here, and let the resultant load act here. Let me put it by dotted line. This is the resultant load. So, how do we calculate position of centroid? Like, let this point be A, B, and C. Like about A, you can take the moment, taking moment about A. So, 60 into 1 plus 80 into 3 is equal to x into r. So what is x? 60 into 1 plus 80 into 3, and resultant load is 240. So how much is x? X is 60 plus 80 into 3 divided by 240. It is 1.25 meters. Now, to get the absolute maximum bending moment, the load should be placed in such a manner that the load and the resultant load, it will be equidistant from the center of the beam. And in such a question, and in such a position, the maximum bending moment will occur under that load. Like there is a load. Let me draw a case.
One clarification, madam. So when two loads are acting, there is no need to calculate the resultant.
No, you could have no in that question. I'll refer back to that question. There, here you are calculating the maximum, absolute maximum bending
Okay.
moment. But in that
Okay.
question, the position of the load was specified, and in that question, you had to calculate that question. Okay, in this question, this question had two loads.
Okay.
And in this question, it was specified calculate the maximum hogging moment.
Okay.
So for hogging moment, you had to place the loads either on the left side or on the right hand side, because only in these two portions hogging moment was getting generated.
Okay. Okay. So
But
if I was asked to calculate maximum sagging moment, then I would put the resultant.
yes,
Okay.
you can calculate the resultant, or you can,
Okay.
when there are two loads,
Okay.
you can directly yes, if there are two loads and you have to calculate the sagging moment, you'll have to use the same technique and calculate the position of the load.
Okay. Okay. Okay.
Either you can use this technique like calculating the resultant, or in that case, mm, no, you will have to use the same technique. There is no other way.
Okay. Okay.
Yes. So, so this x comes out to be 1.25 meters. So the maximum bending moment can either occur under the 60 kilonewton load or under the 80 kilonewton load. So let's first consider the case of 80 kilonewton load. So the beam is 30 meters long, and this is the centroid of the beam. Fine. And how will you place the load? You will place it in such a way that the midpoint of the centroid of the beam, or what, how do I put it? The center of the beam should lie, um, the center of the beam should be equidistant from this resultant load and 80 kilonewton. So this is the centroid of the beam. This is 80 kilonewton and this is the resultant. The resultant is 240 kilonewton. And how much is the distance between this 80 kilonewton and resultant? The distance is 1 point, how much is this distance? This distance is 3 minus 1.25, that is 1.75. 1.75 meter is this distance. So how much is this distance? This distance is 1.75 by 2. It is 1.75 by 2. What is 1.75 by 2? It is 0.875 meters. So how much is this? This is 15 minus 0.875, which is 14.125. 14.125. Okay, this position we have found out. Now, we'll have to figure out the position of the other loads. Now, this 60 kilonewton, what is the, how much far is the 60 kilonewton from 80 kilonewton? 2 meters away. So, place 60 kilonewton here, and one more load which is 100 kilonewton. It is 1 meter away. And how much is this? This is 15 plus 0.875. So it is 15.875. Now you have to draw the influence line diagram. And maximum bending moment under 80 kilonewton, and the point where the position is this point E. So you will have to draw the ILD for this point E. A, B, let me name this as C. So draw the ILD for ILD of bending moment at C. How do you spell it? ILD for bending moment at C. We know the bending moment looks like this. The ILD looks like this. This is ILD for bending moment at C. And we know what is this ordinate. This is AB by L. So it is, what is AB by L? AB by L is 15.875, like A being this length, B being this length, and L being A plus B. So 18 point and 14.125 divided by length is 30 meters. L is equal to A plus B. So this comes out to be 15.875 into 14.125 divided by 30. So it comes out to be 7.474. 7.474. So this coordinate, I'm erasing it. This is 7.474. Now under this load, you'll have to calculate the coordinate, and under this load, you'll have to calculate the ordinate. So let this be x1 and this be x2. So from similarity of triangle, you can calculate this. How can you calculate this? Like 7.474 is here. And how much is this bigger? The base of the bigger triangle is 15.875. This is x1. And how much is this? This is from the center. This will again be 0.875. And how much is this? This is 0.25. 0.25. So this is 15 minus 0.875 minus 0.25. So this comes out to be 6.532. Similarly, you can calculate x2. It will be 7.474 by 15.875. X2 is this ordinate under the 100 kilonewton load. This will be the same number, 15 minus 0.875 minus 0.25, and this is even further 1 meter left to the 60 kilonewton load. So minus 1. Basically, I'm calculating this length. From here, x2 is This is 6.062. 6.062. From here, you can calculate the maximum bending moment under the, you can calculate the maximum bending moment under 80 kilonewton load. It's like maximum bending moment uh, with this position of the load, and the point of concern is below 80 kilonewton. This is what I mean by telling maximum bending moment under 80 kilonewton load. So maximum bending moment with this configuration when it is placed in this manner and the point of concern is below 80 kilonewton. There the 80 kilonewton, where 80 kilonewton is acting, that the coordinate is 7.474. Where 60 kilonewton is acting, you multiply it with x1, and 100 is multiplied by x2. So 80 into 7.474 plus 60 is multiplied by 6.532, and 100 is multiplied by 6.062. From there, you get 1596.04 kilonewton. Now, here what you had considered, this was case 1, that the maximum bending moment is under 80 kilonewton. Now, the same thing can happen under 60 kilonewton. So, you'll have to do this entire thing once again. So, maximum bending moment, considering the case that the point under the point at which the maximum bending moment is occurring is under the 60 kilonewton load. Maximum bending moment at a point where 60 kilonewton load is acting. Let me put it in this manner. Maximum bending moment at a point where 80 kilonewton is acting. So where 60 kilonewton is acting, again, this is the beam A and B. This is the centroid. The entire length is 30 meter. Now 60 kilonewton is here. Resultant acts here. What is the distance between 60 kilonewton and resultant? It is 0.25. So how much is this? 0.25 by 2. The distance between, let's mark only one distance so that it's clear. So how much is this? 0.25 by 2, 0.125. So this is the point of concern. This point, how much is this? This is 15.125. And this is 15 minus 0.125. So this is 14.875. Now draw the ILD of bending moment at, see, this is not C. This point is, this is A. I've written A. So what will be this coordinate? It will be 14.87. This is ILD for bending moment at C. 14.875 plus 15.125 divided by 30. So 14.875 into 15.15 divided by 30. 7.499. Similarly, this is where 60 kilonewton is acting. On the left hand side, there will be the 100 kilonewton load acting, which is 1 meter away from it. And on the right hand side, there is the 80 kilonewton load acting, which is 2 meter away from it. This this is 2 meter away. This is the 80 kilonewton load. Now, then you'll have to calculate the coordinates x1 and x2. If you calculate x1 and x2, x1 will be equal to 6.995 and x2 will be equal to 6.507. Using similarity of triangle, you can calculate this. And again, if you calculate the maximum bending moment under this situation, let's not again use this because this terminology is confusing. Maximum bending moment will again be a 60 kilonewton load into 7.499 plus 100 into 6.995 plus 80 into 6.507. This is equal to 1670 kilonewton. So, in the earlier case, you got around 1596 kilonewton meter, and here you got 1670 kilonewton meter. So, the absolute maximum bending moment is in the second case. So, is this question clear? Okay. Do you have any other questions regarding to ILD, regarding the concepts which I have covered today? Okay. Thank you everyone for attending the session.
Thank you.
Yeah, I'll close the session. Thank you.